Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss with you field theory, msc part 2nd, SEM 4th, and in field theory, second unit is normal and separable extensions. Normal and separable extensions. Unit is subunit is splitting field. Do you know algebraic extensions, field extensions, closed field, closure field? Do you know? In this topic, we study normal extensions and separable extensions. Beyond this, before this concept, we study splitting field. What is splitting field? In algebra from BSc-TY and MSc first, factors of the polynomial do you know? In algebra, group theory, or ring, or modules, factors of polynomial, same meanings in field extensions. Splitting field. Splitting fields means what is splitting field? Splitting fields, yeah. Splitting fields means a polynomial can be factored into linear factor, and in that field, this field is called splitting field. What is definition of splitting field? Let f of x be the polynomial in capital F of x of degree greater equal 1. F of x, degree of f of x, what is greater equal 1 more than 1. Let f of x be a polynomial in capital F of x of degree greater equal 1. Then an extensions k of f, and extensions k of f is called the splitting field. Is called splitting field of f of x over f if this is satisfied following properties, following axioms, following conditions. First conditions: f of x, small f of x, factors into linear factors. F of x factors into linear factor in capital F of x, that is f of x is equal to c into x minus alpha 1 into c minus alpha 2 dot c minus alpha n. This is nothing but f of x is equal to c into x minus alpha 1, x minus alpha 2, x minus alpha 3 dot x minus alpha n, where alpha I belongs to k. K is the extensions of the field E in F. Second conditions, first condition, what is? F of x can be factorized into linear factors. What is linear factors? Degree of this polynomial, this factor, is always 1. Second condition, k is equal to f of alpha 1, alpha 2 dot alpha n. That is, k is generated over f. K is generated over f by the roots of alpha 1, alpha 2 dot alpha n of f of x in k. This is nothing but splitting field. splitting field. Repeat definition of splitting field. F of x is a polynomial in capital F of x of degree greater equal 1, then an extension k of f, then an extension k of f is k of f is called a splitting field of f of x over f, capital F, if first f of x can be factorized into linear factor, that is f of x equal to c into x minus alpha 1 into x minus alpha 2 dot x minus alpha n. It is alpha 1 alpha 2 dot alpha n belongs to capital F, capital K. And second condition, k is equal to f of alpha 1 alpha 2 dot alpha n. This is nothing but k is generated over f. K is generated over f, and by the roots alpha 1 alpha 2 dot alpha n of f of x in k. Remark for multiple choice exam objective questions. The splitting field is the smallest field that contains all roots. Splitting field here, splitting field is a very small field containing all roots. Containing all roots. Here for example, second remark, q of square root of 3. Q of square root of 3 a plus b square root 3 such that AB belongs to Q is a splitting field of x square minus 3 belongs to Q of x over Q. This is nothing but degree of Q of x over Q is equal to 2. Third remark, splitting field of x raised to 4 minus 1, x raised to 4 minus 1 belongs to R of x over R is the field C. Splitting field of x raised to 4 minus 1, x raised to 4 minus 1, what is factor? X square minus 1, x square plus 1. X square minus 1 factors, x minus 1, x plus 1, and x square plus 1, x plus 1, x plus I, x minus I. This is nothing but complex numbers. Therefore, splitting field of f of x equal to x raised to 4 minus 1 over R is set of complex number. One more theorem. There is one more theorem. If k is a splitting field of f of x belongs to capital F of x over f, then prove that k is a finite extensions, and hence prove that it is an algebraic extensions of f. It is an algebraic extensions of f. Now see here, we have given k is a splitting field. K is a splitting field of the polynomial f of x belongs to capital F of x over f. That is k is equal to f of alpha 1 alpha 2 dot alpha n. This is nothing but k is generated over f by the roots alpha 1 alpha 2 dot alpha n of f of x in k by the definitions. That is k is equal to f of alpha 1 alpha 2 dot alpha n is a finitely generated extensions of f, so that alpha 1 alpha 2 dot alpha n are algebraic over f. Hence, by the theorem, k is a finite extensions, and hence it is an algebraic extensions of k. is a finite extension. Next, uniqueness of splitting field. Splitting field is a unique representation of splitting field is a unique theorem or Oedemer theorem. If a k is a splitting field of the polynomial f of x belongs to capital F of x over a field F, if E is another splitting field of f of x over F, then prove that there exists an isomorphism sigma from E to K, that is identity on F. It is given that K is a splitting field of the polynomial f of x belongs to capital F of x over a field F. Therefore, K bar is an algebraic closure of K. Then K bar is algebraic over K. Since K is algebraic over F and K bar is algebraic over F, therefore K bar is equal to F bar. Since E is an algebraic extension of F, by the theorem, the identity mapping lambda from F to F can be extended to an embedding sigma from E to K bar. Let f of x is equal to a naught plus a1x plus dot 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 plus an x to n belongs to f of x. Therefore, f sigma of x is equal to sigma of a naught plus sigma of a1 x plus sigma of a2 x square plus dot 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 plus sigma of an x to n belongs to f of x. Since sigma is identity on f, therefore f sigma of x is equal to f of x. Therefore, f of x is equal to c into x minus alpha I, c into x minus alpha 1 into alpha c x minus alpha 2 dot 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 c x minus alpha n. Alpha I belongs to e. This is nothing but f of x is equal to c into x minus sigma of alpha 1 into x minus sigma of alpha 2 dot 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 x minus sigma of alpha n be unique factorization in k bar of x. But f of x has a factorization in k of x. Say k f of x equal to c into x minus beta 1 into x minus beta 2 dot 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 x minus beta n, where beta belongs to k. It follows that sigma of alpha 1, sigma of alpha 2 dot 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 sigma of alpha n and beta 1, beta 2 dot 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 beta n are equal. Thus, k is equal to f of beta 1, beta 2 dot 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 beta n is equal to f of sigma of alpha 1, sigma of alpha 2 dot 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 sigma of alpha n is equal to sigma of e. Hence, sigma is an isomorphism of e onto